Good afternoon. It's my great pleasure and immense privilege to welcome Professor Ramanath Cowsik uh, as a visitor to the institute. And so Professor Ramanath Cowsik is one of the most eminent scientists of India. He's kind of the doyen of astroparticle physics and gravitational physics in India. And we've known him. I have known about him since the start of my career, obviously as a cosmologist. By the time I started, Cowsik McLennan bound had become textbook thing where, you could, for the first time, say something about masses of particles using cosmological considerations. And that has carried on, and, I'm happy to say the strictest limits on the mass of the neutrinos comes from cosmology at this point. And these are all areas that started with this marriage between astro and particle, and Professor Cowsik has been at the helm of it. His area of specific interest and expertise was cosmic rays, where he spent a lot of time at the Tata Institute. So his career has been at the Tata Institute for Fundamental Research. And en route, he has done so much that I really will spend a lot of time recounting that. But just to mention that near our Gauribidnu field station is a field station where he conducted very, very interesting set of experiments on the fifth force, and also, confirming gravitational interaction at millimeter scales. And this was a big effort with torsion balance. And then, as a director of the Indian Institute of Astrophysics, it was a heroic effort to probably set up something like a 2-meter telescope, the Himalayan Chandra telescope in Hanley. And as I was telling him, with my limited experience with getting things done, I just can't begin to imagine how tough it must have been for him to see this all through. Nevertheless, I don't want to spend all the time here. I should mention that he is, of course, recipient of the Shanti Swarup Bhatnagar Award, member of fellow of all the Indian academies. He's also the foreign associate of National Academy of Sciences in US. And currently he is at Washington University in a named professorship, chair professorship position. And again, it's a delight to have him here. And my request to students is, this is a kind of unique opportunity to meet someone of his stature and kind of enrich yourself. So I would encourage you all to ask a lot of questions, talk to him when you can. With those words, let me invite Ramanath for his talk on how cosmic rays are accelerated. Thank you.
At the outset, I should thank the director, Tarun Sauradeep, for the very kind introduction and invitation to present a popular lecture on some topic of my interest. He launched this series, Vignyana Kathegalu, by giving the inaugural talk himself. So that's an important contribution. And I also want to thank Dr. Subramanian, who is in charge of outreach at the Raman Research Institute, and he's working very hard to see that the research carried out at this premier institute is spread widely, the knowledge is spread widely, not only in Bangalore, but throughout India and across the world through this live streaming lectures. Now I should say something about why I chose this topic of acceleration of cosmic rays as the topic for today's lecture. First of all, even though cosmic rays were discovered about 110 years ago, the mystery of their origins and how these very tiny nuclear particles like protons and nuclei of helium and other nuclei, carbon, and sometimes electrons and positrons, how they gain this enormous amount of energies. What is the process that made them? We know, we have many ideas, but still the origins are a mystery. We have not solved the problem. It's an unsolved problem, and therefore young minds who are gathered here will certainly exercise their abilities and try to solve this problem. I'm going to present a mystery without a solution. And my job today in this lecture is to tell you about it and what ideas have been presented towards this acceleration process, and tell you why we don't truly know the answer as yet. So I want to encourage all the people who are listening to it to exercise their minds towards a solution of this very outstanding problem. It is outstanding not only because it's of interest to cosmic rays itself per se, but also it is the cosmic ray studies, the studies of these particles, that gave rise to other fields of research. At the beginning, the field of particle physics was started by cosmic ray studies, where elementary particles, protons and pions, which are responsible for nuclear forces, were all discovered in cosmic rays, the pion for example, and other particles like that. And very many aspects of fundamental particle interactions were discovered in cosmic rays or hinted at in cosmic rays. For example, parity non-conservation in the decay of the pion. Decay of the kaon was the cosmic ray discovery, but in weak decays, parity is not conserved. That right hand and left hand don't look identical as far as the particles are concerned. So it's a great subject to talk about. But let's come to defining what cosmic rays are. So let me use this and let us see. First, the discovery. How was it discovered? This was discovered somewhere in 1912. Around the same time, Bohr had proposed the model for the atom. He had proposed a model for the atom with a proton sitting very condensed, where all the mass of the atom was concentrated, and electrons going around, and their orbits were quantized according to Planck. And 1912 was the same year that this was discovered also. At that time, we didn't have electronics. The only way we could measure particles was using this device. This is called a gold leaf electroscope. See, these are two gold leaves, and this is a spherical conductor, and it's insulated from this body as it comes down here, this rod. And if this gets charged, these two also get charged, and like charges repel, so that this will open up. So the discovery happened in the following way. It is completely insulated. If you make it wide and leave it alone, it should stay like that. But over a time, it slowly collapsed and came back. That means the charge was leaking away from the electroscope. And the radioactivity was known. You know, Henry Becquerel had discovered radioactivity. They said, so much of Earth is there, radioactive materials are there, they are emitting radiation that comes through the air, penetrates and ionizes the air around. So air becomes conducting, and When you have a conductor, it can carry charges out and gets grounded, so that's why it is collapsing. So people said, let's go up a little bit and see if we go up the Eiffel Tower, for example. That's what the experiment was, that's why I'm referring to the Eiffel Tower. It did go down. So when I go farther from the Earth, sure, it stayed for much longer, charge stayed for much longer. But somebody said, let's go further, let's go so high that charge stays even for a day. And that person who did such an experiment was Victor Hess. The way he did it was, he went on a balloon, series of balloon flights. This is a hot air balloon. And he took that electroscope, he charged it, and he went up. First he tried 1,000 feet, 2,000 feet, 5,000 feet, and so forth. It was decreasing, and by the time he reached about 14,000 feet, roughly the height of Hanley, it started increasing again. And he went up to almost 15,000 feet, and that's where the telescope is. The telescope is located in a hill in the Hanley Valley. The telescope is located in a hill in the Hanley Valley. At that height, it started increasing again. So he concluded, it is true, radioactivity causes discharge and all that here, but there is an external radiation which is coming from outside the Earth, and it is not coming necessarily from the sun. Even at night it is small. So we have evidence for a radiation which is coming from outside the Earth, extraterrestrial radiation, which is energetic and can penetrate deep into the atmosphere, can ionize. Even at 14,000 feet, we have roughly half the atmosphere above us. Even it can penetrate, much more powerful than the radioactivity. Actually, today we know it is 1,000 times to 1 billion times and billion times more energetic than the radioactive particles. That's what was discovered by this. He didn't discover all this. He started the discovery, and over the last several decades, progressive experiments have shown that this kind of a particle comes and produces a shower of new particles as it comes through the atmosphere. And you can see here, and wherever you have the detectors, you see them, and very high energy. A lot of work has gone on, and my job is not to tell you about all the experiments. Let us see what is the spectrum, how many particles are there at different energies, okay? And at different energies, this 10 to the 9, let's go back. Just this 10 to the 9 is an important number. If you take a proton is the nucleus of a hydrogen atom. Its mass approximately is, let us write m proton, 10 to the minus 24 gram, very tiny amount of mass. 10 to the minus 24 means if you take a 1 gram and divide it into 10 to the 24, that is million times million pieces, is this tiny, that's the mass. 10 to the 9 is mpc squared. C is the velocity of light. So these particles are moving almost with the velocity of light, and that 10 to the 9 electron volt is 10 to the minus 3 erg, or many of you who are used to CGS units, this is equal to 10 to the minus 10 joules. Very tiny amount, but still large. Its kinetic energy is equal to its so-called Einstein's rest energy, huge amount of energy. Radioactive energies are very small. They are like not 10 to the 9, but 10 to the 6 is the typical energy of particles emitted in radioactivity. These are 1,000 times, that's the minimum value, at least 1,000 times more energetic, and up to say almost past 10 to the 20, almost up to 10 to the 21. That is, this itself an order of 10 orders of magnitude, 11 orders of magnitude more energetic. 11 orders of magnitude means 100 billion times more energetic than the minimum energy, or almost a million times the energy of a radioactive particle. So you can see it's a very fascinating and very energetic kind of stream of particles that are coming in. And if you have, for example, a mustard amount, just the size of a mustard of cosmic rays, of this minimum energy, how much can it do? If you have an all-electric home, let us say, for 1 year, it can supply enough energy for your heaters, your air conditioners, and even for cooking electric stove, 1 mustard seed of cosmic rays. But unfortunately, or fortunately, the amount of cosmic rays is so small. If to gather 1 mustard seed of these particles, you have to take a volume, huge volume, because these particles are spread out, very low density. So we can't collect 1 mustard seed, and we can say and solve these of course, these particles are so energetic. If you have a mustard seed of them, it can supply energy to the whole humanity for 100 years without any difficulty. But they are so small. Look at this order of magnitude. Some 10 to the 4, here already 10 to the 26. So it's a 10 to the minus 26. It's a very, very, very low density. 1 followed by 26, 0 below 1, you see. Something like that. 1. My hands pain, I can't write so many, you see, like this. It's so much. So it's very tiny amount of particles. So let us summarize what they have, and let me go to the next slide. So minimum energy is so much, maximum energy is so much. So 1 milligram, that is typically a mustard seed, can evaporate all the waters of Krishnaraj Sagar if you want to. And a bomb made of minimum energy cosmic rays is at least 1,000 times more energetic than the most powerful atomic bomb. Fortunately, cosmic ray density is very small, as I said, so we will see. Where are they located? They are located not we see here, but they are also located in other places in high concentrations. What is shown here are pictures of what are called as supernova remnants. What are supernova remnants? Supernova remnants are the products of explosions of stars. Stars, especially massive stars, which are say 10 times more massive than the sun. Sun itself is very massive, of course, but 10 times more massive stars, they, near the end of their lives, they explode. the debris flies apart with a lot of energy. And as it plows through the interstellar medium, some processes happen that produce these energetic particles. And the way we see them, these energetic particles can radiate. Suppose you have energetic electron, it can produce radio waves by moving in magnetic fields. It can emit gamma rays by a process called bremsstrahlung when it passes through matter, and it can emit X-rays, all kinds of things it can do. Same thing the proton. Proton does not emit radio waves, but it produces this neutral pion, or which is responsible, these are responsible for nuclear forces, and this neutral pion called the pi 0, it decays and gives you powerful gamma rays. So you can see them in gamma rays and so on and so forth. And not only from these sources, but you can see them from our whole galaxy. See, our galaxy is huge. Those from here, if we send a signal to the sun or some signal from the sun starts, it takes 8 minutes for the light to come from there to here. Not going back. Yeah, the size of these, light takes about 10 years to go across. From here to the sun is 8 minutes. To go across this, it takes 10 years. For light can go around the earth some 100 crore times in 1 second. If I send a light, even it's going around, so 100,000 times it can go around. It's very fast. Not 100,000 times or something of that sort, huge number of times. It's very fast. So to the sun it takes 8 minutes. Across this it takes 10 years to go, even for light. Motor car will never cross this. You don't have enough time. The motor car will be all broken down before you can cross it. And in the galaxy, it takes 30,000 years to cross the galaxy, from here one end to the other. From here to here takes 30,000 years. So it emits in radios in this particular way, and Raman Institute carries out extensive work in this field. It's one of the most famous laboratories in the world which works on radio waves, particularly from the cosmos. And gamma rays also it comes. So cosmic rays are everywhere, near the earth, certainly throughout the solar system, certainly in these sources like supernova remnants, in all our galaxy, and indeed not only in our galaxy, I mentioned these things, and in supernovae, which we saw some pictures, in pulsars, black holes, everywhere. These energetic particles are unique and ubiquitous. Ubiquitous meaning everywhere. And they are even made, some small, very tiny amounts, very low energy ones are made even in the earth. The solar wind comes and hits the magnetic field of the earth, and it pulls the magnetic field, and you can see cosmic rays being accelerated in that tail. Not only in our galaxy, this is a picture of a supernova that went off in the Magellanic Cloud. You know, the Magellan, who navigated to the earth in 1500s, he saw these clouds, and one of the stars in that cloud exploded just in 1987 and created all this very interesting phenomena. Just to describe this figure fully and explain it, it will be another talk. So we will not, like Mahabharata, you see, you start telling a story, Bhima did this, and suddenly Ghatotkacha's story comes in. Things like that. And here is a black hole. Here is a black hole, and it is producing jets of energetic particles. And this jet, this distance, it takes almost 1,000,000 years, hundreds of thousands of years to go, light to go from here to here. This beam of energetic particles which are traveling almost with the speed of light are traveling like that, and they get slowed down and get scattered and make these big radio sources, huge distances. These are the distance to this object itself. Light will take 1,000,000,000 years, 1,000,000,000 years to go from here to there, of that order or more, maybe few billion years. Billion meaning 10 to the 9, 100 crore years. More examples of such beaming, and this kind of jets come out of black holes. See, that's what we were seeing, and jets in other systems which have produced these radio sources. Here, like this. So, little thing about the pulsar. Let us see if we can play what pulsars are. Pulsars are rapidly rotating, exceedingly condensed objects called neutron stars. Its density is same as that of nucleus of an atom, but it's as massive as the sun. And size of the sun condensed to that density will be smaller than that of the earth. It will be like from here to Jayanagar. That's the size of a neutron star. Let us see what it does.
A pulsar is a rapidly spinning neutron star, which is the small, incredibly dense remnant of a much more massive star. A teaspoon of matter from a neutron star weighs as much as Mount Everest, and a neutron star is so compact that a ball about 15 miles across contains more matter than our sun. Neutron stars spin between 7 and 40,000 times a minute and form with incredibly strong magnetic fields. Rapid spin and intense magnetic fields.
So that's a neutron star. They produce a lot of particles, energetic particles, by this magnetic field rotating and all that, as he was saying on the commentary. So more black holes, more things, just wanted to show you. And in the centers of all galaxies, this, let us say it's our galaxy, there is a black hole sitting there. Most spiral galaxies have a very massive black hole with mass more than 1,000,000 times the solar mass, 1,000,000 times to 100 million times the solar mass objects. So what is the average energy density of these particles? Even though individual particles are very energetic, the energy density, that if you take a small 1 centimeter cube volume, so much, little bit of a spoon of interstellar medium, what's the energy in it? Is 1 electron volt. 1 electron volt is 10 to the minus 12 erg, or 10 to the minus 19 joule. That's the energy density. So if you want 1 joule, you have to collect 10 to the 19 spoons of that, and it's not possible. 10 to the 19 means 1 followed by 19 zeros. You have to always keep these big numbers in. Whenever you do astronomy or particle physics, big numbers and small numbers keep coming. You should get used to them, not to be daunted by big ones, not to be supercilious about small ones. So you can see, oh, I have written those numbers there, I didn't have to write here. And you can find out how long cosmic rays are there. What happens is sometimes the cosmic rays leave the galaxy and go into the intergalactic medium. You can think of a bucket with a hole there and you are running water, okay? Of course, water is running out. If you run it very fast, the water will rise to some height. If you make it even faster, it will go to greater height. So by measuring the height of the water and knowing how much is the stuff coming from the tap, you can estimate the size of this hole, how much it's leaking. Or you fill the bucket and you remove your finger from that hole, and it takes 10 to the 7 years for all the cosmic rays of that order, maybe between 10 to the 6 and 10 to the 7 years, rough numbers, for it to all leak out of the galaxy. So we know to develop this density, what is the power that is needed. This is how much source energy we want, how much source, what is the generation, energy generation rate that we need to keep all these cosmic rays at this present level of density. That's the kind of question that we want to ask. Of course, there are magnetic fields in the galaxy which also have roughly the same energy density, and they keep the cosmic rays in for this 10 to the 7 years, because cosmic rays don't move in straight lines in the presence of magnetic field. In the presence of magnetic field, so let me clean this up a little bit. What cosmic rays do, let us say these are the magnetic fields like this. Magnetic fields are like that. Cosmic rays will move like this, in spirals like this. Occasionally the magnetic field direction may change here. That is, when you do this, magnetic field direction will change. When it comes here, then it will start doing this kind of thing. It will get scattered. So we can't, by measuring cosmic rays, we can't tell it is from this direction is the source of cosmic rays. We can't tell. It's all jumbled up before it comes here. We see sunlight, so we can tell where the sources are. Here, by looking at cosmic rays, we can't tell which way the sources are, where the sources are, which is the nearest source. We can't tell. That's why the mystery. So how much power should the sources have? If you know 10 to the 7 years for it to leak out, and how much is the density, divide one by the other, you will find out all that. So it's all numbers I have done. I know the volume of the galaxy, how big the bucket is, and what's the amount of water in it, that's how much cosmic rays are there, and divide by 10 to the 7 years, that is the amount the faucet, the tap should give, so much rate at which it has to fill. So that number is here. 10 to the 48 erg per year is what you want to generate. The supernova explosions, they generate total of 10 to the 51 erg, just about 100 or 1000 times more energy, but this is ordinary garden variety energy, not in high energy cosmic rays. So you have to be very efficient to generate so much power. Somehow the kinetic energy of the debris of the explosion should be communicated to energetic particles. How do we do this? That's the question. It should be very efficient. For answering this question, we will see how man accelerates cosmic rays, not cosmic rays, energetic particles, in the laboratory for experiments. Here is Ernest Thomson. He devised a method in 1937 or 36. Two magnets are there, electromagnetic is there, and some small amount of radioactive particles or something, or an ion beam is produced by some electric field and enters this region, and this magnetic field ramps up. Changing magnetic field is an electric field, and that accelerates these particles to higher and higher energies, and it comes out, and that is the trick by which this is done. But in space, nobody is doing this. No electric fields in space, because as I said, air itself is conducting. Interstellar medium is also even more conducting than the air. For the size, it can conduct away. If you put a thicker copper wire, more current will flow. So you can't have electric fields there. And the best cyclotron can produce about 10 MeV, that is 10 to the 7 electron volts. That is of the order of 10 times more than the typical radioactive particles that will come out. So man built a bigger accelerator. This is in Geneva. See the big accelerator here, it's about 30 kilometers ring. Other one was kept inside a hall. This one was a long tube, and in that tube, of course, various magnets were there. You can see these are all magnets, and straight section and a magnet. It will bend a little bit, next straight section and a magnet, and the particles can go around. So it's like a huge synchrotron, a huge cyclotron, but without changing the magnetic. It's all constant magnetic field. But inside this tube here, you have microwaves going. Microwaves are, you put your stuff here, you can heat it up. And the way they heat it up is microwaves have electric field that moves the electrons inside and heats up whatever you have. Here, they adjust the electric field to be in phase with the particle. The particle always sees the accelerating electric field. It doesn't oscillate, it keeps moving in the same direction. So the microwave goes like that and accelerates the particles throughout the system. They keep it in phase. That's why it's synchronous. That's why it's called a synchrotron. And you can go up to, say, 1000 GeV, 10 to the 9 electron volts, almost a million times more energetic than the radioactive particles. No electric fields in space, magnetic fields are there, they extend over large volume, but efficiency should be enormous. Man-made accelerators have efficiencies of the order of 1 part in 10 to the 5. That is, you have to spend almost a megawatt to get 1 watt of energetic power, particle power. So this has to be much more efficient. How is that done is the question. That's the challenge. So no electric fields. Now people started thinking, suppose I take some very cold air and leave it here, what will happen? Other air molecules will come and hit against that. The cold molecule will gain some energy because it's being hit by a hot molecule, and they will share energy and equilibrate. This process can heat it up only up to the temperature of this air that is around, not much more. So this process will not do, and the distribution is some kind of an average of the whole thing, and it's called, those of you who already come to college will know the Maxwell-Boltzmann distribution. It's kind of some typical energy is there, there's a temperature, a few times the kT energy of the individual particle, the number of particles goes to almost 0. So this process of that kind of thing cannot happen. What is the solution? We are going to use collisions, but in a very special way. The interstellar matter or the debris from supernova remnants, they are in lumpy things, they are not smooth things, and those lumpy things are tied up by magnetic fields. You can think of magnetic field as kind of some rubber bands or the strings across a tennis racket. Whenever tennis racket moves, it carries the magnetic field and it has to move. Carries the string and moves. And when the ball comes and hits, it need not necessarily hit the frame. It's not some small region. The whole mass of the frame is the thing that is experiencing the collision. So this trick is what is going to be made use of. And their masses are huge. So masses are, you can see, tend to be more massive, 10 times more massive than the sun to 1,000 times more massive than the sun. And their velocities are about 10 kilometers per second. 10 kilometers per second is kind of supersonic jets, like rocket speed, but not like the speed of light. You know, if supersonic things are there, but light can overtake it in no time. If you have a light gun, you can shoot a supersonic plane down. Laser gun, people who are developing all that kind of stuff. So, but what's the energy it has? Each cloud has an energy of 10 to the 46, 49 ergs. This is much more than the millions, billions, and 10 to the 20 times more energetic than, 10 to the 40 times more energetic than the cosmic ray energies. So it has a lot of energy, but all in dull fashion, slowly moving. So many collisions may do this. This idea was proposed by a famous scientist by name Fermi. I think I have a picture of him. See, this is Enrico Fermi. He is the first man to make controlled fusion of, fission of uranium in Chicago. It was long ago. Enrico Fermi. This is Heisenberg. He developed a full-fledged theory of quantum mechanics. And this is Pauli, another great scientist, all Nobel Prize winners. And Pauli told that the electrons and some particles like that have spin. They are spinning particles. And he gave the idea. And also about the neutrino. He proposed that the neutrino should be there. But they are all three sitting and chatting away, but it was Fermi. And his idea was that these clouds are there and cosmic rays come hit. Sometimes they lose energy, sometimes they gain energy. On some few particles may go off to very high energy by chance. They have always been gaining a little bit each time and so forth. That was the idea. Something like a pinball machine that, I don't know whether you have seen this. If you press a button and lever, some ball flies out and it goes, you can keep on playing with it. It's kind of a game, and he's used to that. Or in Italy, they have all this lot of interesting games to play, and this hand football and all that kind of thing they have. So let us see. I want to show you some example how it can work. Let me see if I can do this.
Обводочка, давай, давай. Ну, гаси, гаси. Вот это да, вот это да. Вот это мощно. Я вообще в шоке, Кал. Красавчик. Обводочка, давай, давай. Ну, гаси, гаси.
Thank you. So, that is Fermi acceleration. This can work in some places. And inside supernova remnant is so turmoil, so much is happening, everybody is running every which way, it can happen. Interstellar medium is much more sedate place, you see. These clouds are going like this. 10,000 kilometers per second is the speed of the debris in supernova remnants. The interstellar clouds are moving only 10 kilometers per second, not 10,000 kilometers per second. So this equation that is written there is just describes that process completely. And that if you solve, and calculate how much radio waves are coming from this Cassiopeia A, you can fit the spectrum very nicely. So it may happen, this kind of process may be occurring in supernova remnants, but certainly not for generating cosmic rays. So one has to think of a more efficient system for accelerating cosmic rays. Imagine the following thing. Let us say we have a fast flowing gas here or something, interstellar gas or whatever, something carrying magnetic fields and all that kind of thing, it's coming, and suddenly it goes through some kind of a transition, and after the transition it is moving slowly. After the transition it's moving slowly, before the transition is moving fast, but it's carrying the same amount of material. If it moves slowly, it means its density has gone up. Suppose we think of such a situation, and let us see what happens to a particle which gets bounced around this transition. This transition region is called a shock, and this is very well known phenomena. For example, when an airplane goes through air, when it crosses the sound barrier, it is moving faster than the air molecules can adjust to each other, and this kind of phenomena occurs. That's why you hear that boom, sonic boom. Many places this occurs, and let us say what happens to collisions between this and some kind of a magnetic field bounce off, like a trampoline or some, for a jumping activity. Take a small amount of energy to start with, E naught, and it goes onto this, and it is, the fluid is moving in this direction, gas is going in this direction, but it bounces back. That is, he's doing a drop shot in a tennis. That guy hits reasonably fast, but he does this and it just goes and falls like this. He has to come and then hit it again. You understand what's happening? It's got slowed down, but this guy here, I pressed a bit too hard. Okay. Not used to it yet. Okay. Thank you. Next one. Next. Okay. And what happening here? He hits it again very, very hard. But this has some velocity. Hits it again, and this comes out with even greater speed on this side. So you can see what's happening in the match. He hits it very hard. That fellow does that, and it goes, and hits it again very hard. He does that, it comes out a little faster this time, next time. Even though he's trying a drop shot, he can only do that much. It comes there, and he hits it even harder. Every time you hit it, not only energy of the ball is reversed, you add the speed with which the racket is moving. Every time you hit, it's gaining more and more energy. I don't know whether you have noticed it. In the beginning, it's small. It's like that you can't, even the maximum force you had to hit, stationary ball, you can't hit it as fast as you are returning a very fast incoming ball. You are adding this so much extra every time you hit a fast ball, you add this extra velocity of your racket to the thing. Because this racket is so heavy, it is not stopped by the ball. In its frame, it is giving back the other way, but the frame is moving. Your racket is moving. So you keep on increasing the energy of the particle continuously in this fashion. And I think here is an example. What's happening? Maybe you can.
Time is in turning the corner.
Anyway, it becomes faster and faster, and that's the story. So this kind of a thing can occur. There's a possibility, it's called shock acceleration, and that's possibility. And sometimes shocks can occur around condensed objects like black holes. Suppose there is a lot of material coming and falling. Here's coming, as it falls, let us say I take a big blob of material and drop onto the earth, it becomes faster and faster and faster, and velocity goes to zero once it hits the earth. So you have a similar situation as this fast wind coming and becoming a slow wind afterwards. So around a black hole such things can happen, and you will have a shock which looks like that. The mathematics of that is kind of hidden in this formula, and you can solve what happens to cosmic rays in such a thing, because here continuously energy is coming in, falling in because of the gravitational field. There is no inexhaustible source of energy, almost inexhaustible source of energy in this fashion. So it keeps coming, and this can be accelerating particles to high energies. So you can see this kind of thing happening actually around some supernova remnants, and it happens everywhere, and experiments are going on. So let us summarize. Cosmic rays are very energetic particles. They are everywhere. They are raining down on us. Huge amount of energy per particle, but their average energy density is very small. Most probably they are accelerated through this mechanism which we discussed near the end of the lecture, the shock acceleration. That is where a fast moving plasma, magnetized plasma, is coming and moves after the shock with a source speed. Every time a particle crosses that shock, it gains some energy, and repeated crossings, it keeps on gaining energy and sometimes can escape that system, and that's what makes cosmic rays. Like that football tore through the net and went out, it can go out of play in that way. From this acceleration, very energetic ones can escape, and that is cosmic rays. But this is a conceptual idea, but the mystery is not yet solved, and I want some of you, for listening to all this, or many of you, to focus on this very important problem. It was the problem of the last century. Scientists like me could not solve it. Now scientists of this century, you have got to solve it. Thank you.
So thank you, Professor Cowsik, for this fascinating talk and for the open challenge to all the young scientists. So we open this for questions.
Good afternoon, sir. So I have two questions. The first one is pretty basic. If you go to the all-particle spectrum that you showed, so the spectral data points in near 1 GeV to 1 TeV, it's pretty much it's all right. But in the high energy, really in the EeV to ZeV region, since those particles have very ultra high energy cosmic rays, so the probability of detecting them should be very small, right?
Yes.
But the density of data points in that all particle spectrum is pretty high in the ultra high energy cosmic ray region. But in the middle, near 1 TeV or something, the data points are really scarce. Is there any particular reason for that? You can visualize if you can just see that.
Somewhat of a technical question. Let us see what you're asking. Yeah.
Yes, yes. So the data points in the ultra high energy region is pretty dense.
Yeah, here is you are talking about somewhere in this energy.
Yes,
region?
yes, near 1 TeV. So
Yeah,
the scarcity is.
what's the question?
This technically the ultra high energy, the probability of detecting
Here.
the ultra high energy should be very low, but there again the data points are really dense in the very ultra high energy, like near 10 to the power 18 electron volt, 10 to the power 21 electron volt.
Yeah, you're asking what's happening at 10 to the 18?
Yeah, in general, the data points should be scarce here because the probability of detecting that high energy cosmic ray should be lower, right?
Yeah.
But the density of data points is very high in that range, whereas in the middle range, the data points are really scarce.
Everywhere, you know, the energy density of these particles is continuously decreasing.
Yes.
Nowhere it's going up.
I'm talking about the scarcity of data points, just the data
Oh,
points.
density. Why this density of data points is more here?
Yes.
You see, people, as you go to higher and higher energies, you want to, different techniques are used for the detection of these particles.
Right.
Okay? And that region of great interest, large number of detectors are there. They detect them using a method called extensive air showers. Very energetic particle comes, it produces some neutral pions and charged pions and other particles. Neutral pions immediately decay, giving you gamma rays. Gamma rays make electrons and positrons, and they give you more gamma rays, they make electrons and positrons and so forth, and the whole shower develops. People can measure the particles themselves on the ground, or sometimes the Cherenkov light emitted by those particles. So they have detectors and telescopes, small telescopes, looking at the sky, and these things are events which are like a spike. It comes and almost with the speed of light, it crosses that, and it's a sharp spike in light they will see, and by coordinating that they can reconstruct this and they can measure this. That's how those particles are measured. That's why people are very much interested in those highest energy cosmic rays. They have measured more and more in all this kind of way. That's why the density of observations are more, not the density of particles is more. Its density of observations is more.
Yes. So another question. You explained that Fermi second order. Initially, you explained the Fermi second order acceleration. It's a bit technical question. I wanted to ask about your opinion. Do you think that this passive GMCs, in which supernova is not associated with those GMCs or any molecular cloud, let's say. So, do you think that the cosmic ray that enters those passive GMCs can get reaccelerated to again a very high energy and then get out of that GMCs? I mean, do you think reacceleration is possible inside GMCs or in general inside galaxies?
Yes, of course, it's happening. They are continuously being accelerated, and you know, they can get reaccelerated, surely.
Reacceleration, you think reacceleration is possible inside passive GMCs due to that electromagnetic turbulence?
Sorry, I did.
Do you think that due to electromagnetic turbulence inside passive GMCs?
I couldn't quite make out what you're saying.
Electromagnetic turbulence.
Electromagnetic?
Turbulence.
Turbulence.
Yes.
Yeah, it's a magnetic turbulence. Yeah. Of course, in turbulence, they are continuously being accelerated. And acceleration decelerations are not of equal value because the chance of, if two particles are moving in the same direction, the chance of collision is smaller. If they are moving in opposite direction, the chance of collision is higher. So head-on collisions are more than overtaking collisions. And because of this reason, cosmic rays get accelerated. This difference, tiny difference between the two, is what makes for particles to go to high energies.
It is possible to get, very, like let's say, 1 TeV energy inside molecular clouds?
Yeah, small numbers, depending upon how long it stays there, you can get, it's not impossible.
Right.
But probability decreases because this difference between the two is small, and slowly it's gaining energy, and if it leaves the system, then that's the energy. So since things are leaving, depends upon how long it stays in that system, that determines the maximum energy that you can.
So let's assume it's a giant molecular cloud, not just a molecular cloud, so it's a very big system, and that way the particle will have more time to go around inside the GMC itself and get reaccelerated to very high energy. So you're saying that it is possible?
This is possible, but I don't know how probable, that's all.
Very stimulating talk. Hi. So my question is related to the shock theory. So if I understand that older cosmic rays will be less energetic if they are going through many more shocks.
No, older cosmic rays, there is more, those...
Older cosmic rays will be more energetic,
yes,
because they have gone through many more shocks than the newer one.
Correct.
Now suppose you try to do a G2 type of a measurement, that time correlation of the cosmic rays which is arriving.
Yeah.
So do you have a way to validate the...
Know where they are coming from. Let us say some particle center, those who stayed for a short amount of time got less energy and came out. Those that stayed for a long amount of time got more energy and came out. But when they came out, we can't tell. It's going, this particle might have scattered here more quickly and come, the other one might have come later, and this process may be ongoing. In some regions, the time constant for all these things happening is tens of thousands of years, and there may be many places this is happening, and we know that the cosmic rays that we measure are more or less constant in time. Over millions and millions of years, we can say the average rate at which cosmic rays are coming has not changed by more than a factor of 2 for millions of years. So you see, the big galaxies are being made in many places, coming time correlation, just like there is no direction correlation, there is no time correlation, precise time correlation between when it was produced and when we see it. There is a kind of a statistical correlation, but if you have many sources, they all merge out and they smoothen each other out.
Okay, so what you are saying is that if we knew a specific source, then there could be a time correlation which could validate the...
Yeah, in principle, there again, as I said, even if you know from this particular source, it's not clear how many crossings, even the crossing is a statistical process.
Right.
It is not that if you cross, immediately it will scatter. Some may go farther and get scattered.
Mm-hmm.
That is, when you are walking in a crowd, some people may dash against another person very soon and they may go back. Some people may be walking more, not intentionally. In a crowd they are walking, some people move more, some people move less, and wiping out, the smoothening because of the statistical nature of the process.
How much would it...
So my question is, how important would understanding the galactic magnetic field structure in detail help in the cosmic ray problem solving?
It's very important, and the way galactic magnetic fields are understood are using pulsars and extragalactic radio sources. You can measure how smooth the magnetic field is and what's the strength of the field, and these things you can measure cosmic rays, I said, when there is a little kink or something in the magnetic field, they scatter there. So, quantitatively calculate how much scattering has occurred, we need to know the magnetic field very precisely. And second reason, even the average field is important. If you have a field of some strength, the cosmic rays go around this or this thing like in accelerator. Bigger the accelerator, higher is the energy that you can contain in those magnetic field. So the galactic magnetic fields can contain up to about 10 to the 16, 10 to the 17, even up to almost 10 to the 18. Beyond that, these cosmic ray particles will bend very little in the galactic magnetic field. You may be able to see extragalactic sources. That was one of the reasons a lot of effort is being put in to see extragalactic sources of cosmic rays. They bend a little bit. I know the magnetic field, so if I see it in this direction, then I will say it has come from that direction. You can make some calculations of that sort. So magnetic field is a very important ingredient in cosmic ray physics, especially because the average energy density of cosmic rays is same as the average energy density of the magnetic fields. They are roughly balancing each other. A process which is called equipartition in technical terms.
So I have a question. As you told that there are several mechanisms for acceleration, and I mean, as you told that it is an open question. I mean, as a complete theory, what I mean, what is the characteristics of as a complete theory of acceleration? Because already there are energetics of various sources which are producing cosmic ray particles, and there are
the
also.
thing is, acceleration is one aspect of cosmic rays. You have to explain how many protons are there, how many helium nuclei, how much lithium, beryllium, boron, carbon, oxygen, neon, aluminum, sodium, etc., and iron, and so on and so forth. You have to explain that composition. And you have to prove that this is really the process which accelerates the cosmic rays. This shock acceleration is a process which can accelerate cosmic rays. Are the cosmic rays accelerated in this process? I don't know. But we can accelerate. It's a candidate. It's a candidate for acceleration process. We hope it's the right candidate, but we don't have a proof that it is indeed this process that led to cosmic rays. That's what I'm trying to say.
So we request Professor Sauradeep to give a small token of our appreciation to Professor Cowsik.
Thank you.
Wonderful to have you visit.
Thank you.
Hope to see you visit more often.
Yeah, thank you. Thank you all.